Reinforced cement concrete. Plain cement concrete is a mixture of 4 ingredients, namely cement, water, fine aggregate, sand, and coarse aggregate. Concrete is good in compressive strength, but it is very weak in tension. So whenever stresses come into tension zone, a support is required to enhance the performance of the member. Such enforcement or support is created by high-strength steel bars, and the concrete becomes plain concrete to reinforced cement concrete. What is a singly reinforced beam? Beams may be simply supported at ends or may be continuous over spans. Ends may be fully rigid, semi-rigid, or may be flexible. Any of the case, all types are considered as flexural members, as bending dominates under loading. When a flexure member bends, top layers experience compression and bottom layers experience tension, but there is a layer over which neither tension nor compression exists. Such layer is obviously called neutral layer. It depends upon the end conditions and loads with respect to neutral layer, upon which upper fibers and lower fibers would be under tension or compression. As we know that concrete is weak in tension, so we provide steel bars in tension zone to minimize cracks development. Such an arrangement with steel reinforcing bars in single tension zone is called singly reinforced mechanism, and such beams are called singly reinforced beams. Framework of reinforcement. There are two types of supporting frames generally used for any structural member designed as per Indian standard codal provisions. The major framework is called as main reinforcement, and the minor framework known as distribution or secondary reinforcement. Beams have longitudinal bars in tension zone as main reinforcement and rectangular rings known as stirrups as secondary reinforcement. Main reinforcement bars are used to enhance strength in tension zone, while stirrups are used to cope up with shear stresses developed due to bending. How do we calculate strength of a singly reinforced beam? Strength of beam is calculated in terms of moment of resistance. Moment produced by force coupled, compressive force and tensile force, is termed as moment of resistance, denoted as Mr. Moment of resistance Mr should be more than the calculated factored moment denoted as M, at most critical section of beam due to external loadings. Mr should be greater than or equal to M. Mr equals moment of resistance of the given section of beam. M equals factored design moment as an effect of external loading.
The stress-strain curve of concrete is obtained from experiments over many cubes. It has following salient points. 1. When load is increased on the specimen, the stress-strain curve is parabolic up to strain of 0.002. After that it becomes straight line to reach ultimate strain before failure equals to 0.0035. 2. The ultimate stress taken by concrete cube ranges 0 to maximum value of FCK. The factor of safety taken for concrete is 1.5 to accommodate variations on site and other quality reasons. For design purpose, the compressive strength of concrete in the structure be assumed to be 0.67 times characteristic strength. The partial safety factor gamma MC equals 1.5 shall be applied in addition to this. So final stress taken by concrete in compression is taken as 0.446 FCK. Figures 1.2 and 1.3 show the representative stress-strain curves for steel having definite yield point and not having definite yield point, respectively. The characteristic yield strength Fy of steel is assumed as the minimum yield stress or 0.2% of proof stress for steel having no definite yield point. The modulus of elasticity of steel is taken to be 200,000 N per square millimeter. For mild steel, the stress is proportional to the strain up to the yield point. Thereafter, post-yield strain increases faster while the stress is assumed to remain at constant value of Fy. For cold work bars figure 1.3, the stress is proportional to the strain up to a stress of 0.8 Fy. The two grades of cold work bars used as steel reinforcement are Fa 415 and Fa 500 with the values of Fy as 415 Newton per square millimeter and 500 Newton per square millimeter respectively. The tensile strength of the concrete is ignored. The stresses in the reinforcement are derived from representative stress-strain curve for the type of steel used. Typical curves are given in figure 1.3. For design purposes, the partial safety factor is equal to 1.15 shall be applied. The maximum strain in the tension reinforcement in the section at failure shall not be less than 0.87 Fy upon As plus 0.002.
For complete course and step-by-step illustration, please subscribe full course on Structural Analysis and Design app. Also subscribe YouTube channel Maatrixx Digital Solutions. Thanks for watching.